All right, great. Thank you for the introduction. My name is Chris Rohlf. You can yell at me on Twitter down there on the bottom right, which is Chris Rohlf. My talk today is on effective memory safety mitigations. This talk is mostly through looking at mitigations through the lens of an exploit developer. I spent most of my career in exploit development up until I joined Square, and I started that around 2003. So I have a lot of years of experience of writing exploits under what I would consider favorable and fun conditions back in 2003, when essentially getting arbitrary code execution was quite trivial, and you could do it on really interesting and hard targets, or easy targets for the time. Today I'm going to focus mainly on user space memory safety mitigations. So there's like a whole class of mitigations for kernel exploits we heard a little bit about in the previous talk. I'm not really going to talk about any of that today. It's mostly going to be concentrated on user space. And the general theme here I'm going to be revisiting is what mitigations are effective and why they're effective. So that's a reoccurring theme throughout the talk. But I really can't do that until I give you some history up front, so I'm going to start with that. There's no way I could cover all the exploit techniques over the years or all the mitigations over the years, so some things I'll gloss over. If you have any questions at the end, feel free to ask me or talk to me afterwards. I'm going to talk about some of the major new exploit mitigations that are more generic and being applied to hard targets like browsers. I'm going to talk a little bit about a custom mitigation I've developed called ForkGuard. And we're going to talk a little bit about how programming languages and program design can affect how effective your memory safety mitigation is. So first, a quick note on native code security. I know there's like 5 people in San Francisco who think Rust is like going to be a thing, and I'm sure it will be. I'm sure it totally will be. But in the real world, C and C++ are very heavily relied on to this day, despite 20 years of Java enterprise apps and the fact that every CI/CD system is basically Bash, Python, and Ruby just kind of mashed together and somehow it works. We still rely on C and C++ for everything from operating system kernels to mobile applications to email readers, you name it. A lot of things are written in C and C++. So native code security totally still matters. And clearly, none of us would be here today if we had gotten this right 10 years ago. But that's not to say that there haven't been improvements over the years. There definitely has been. The tools we use to build, our compilers, our libraries, the static analysis tools, things like address sanitizer, all these things have gotten better and better and better. The problem is that the rate at which we crank out this code just really can't keep up. And if you've ever followed along the development of things like WebKit, for example, you know that it doesn't matter how many cores that Google or Apple throw at this. The amount of new code that's added to it. New bugs are introduced all the time. So this is an ongoing problem. So memory safety vulnerabilities are still a challenge. So I promised you a brief history lesson. The small text, of course you can't see, probably, is on the bottom right. It says it's an incomplete timeline, and please consult your local hacker historian for more information. But I tried to capture as much of the main themes as I could. Back in the pre-Cambrian era of exploitation, pre-2000, we had everything in the late 80s, early 90s that focused on basic stack overflows. And this was a really fun time where you could just smash a saved return address and get arbitrary code execution on a root DNS server. Not that anyone ever did that, but you could. We had things like SplitVT, who one of the authors may or may not be here today, I think. Saw him yesterday. Smashing the stack for fun and profit. Everyone's familiar with this famous Frack article. And because of these exploit techniques, we saw an emergence of mitigations. Things like a non-executable stack, like stack canaries. And it sort of upped the game for exploit developers. We have to get around that now. What about this heap thing? That might be vulnerable. We might be able to do something with that. And so the heap era sort of took hold, right? And that started in the early 2000s. We saw famous Frack papers like Voodoo Malloc tricks. These were like papers that if you haven't read, you should go back and read them just for historical purposes. They don't really apply today. But as I'll get to later in the talk, you'll see that the concepts still apply, even if the specific code patterns no longer do. But it was in those early years of the 2000s that we saw things like address space layout randomization. If you're not familiar with that, it's basically a technique where you shift around all the different parts of memory per process, and so things become a little bit less reliable. You can no longer rely on your stack always being mapped at a specific location or your heap being at a specific location. And then we entered the 2005 to 2010 era. And this was an interesting time when browser exploits really exploded. We saw really cool stuff like heap spray on IE6 and flash techniques, and this was like the Wild West, except there were way more people to own, and you could own them directly through their client. But it was also the beginning of the end for general exploit techniques. Those early papers like Voodoo Malloc tricks no longer applied. And things started to get a little bit harder when it came to using generic techniques to get arbitrary code execution. We also saw the emergence of ROP, return-oriented programming, or I should say the formalization of ROP, which was originally return to text many years before that. And in this time, we entered an era where memory disclosures started to be required for really hard targets because you had things like ASLR. So we fast forward a little bit, things get harder and harder and harder, and it kind of brings us up to present day, where side channels, of course, break everything. Like the talk this morning was amazing, and every time I think about it, I wonder, like, what are all of us doing? Like, we should be back at the office rewriting everything from scratch because none of this is all for nothing. So things got harder and harder and harder. Kernel protections become the default. We have things like execute-only memory on newer ARM chips. Sandbox escapes are required for any serious target. And as we can look a little bit ahead to the future, we can see that CFI and CFG, and I'll talk about those later, those are becoming standard. They're going to be hardware assisted in a few years. We have things like immutable containers and sandboxes that throw out the process the second you touch it. We're going to have things like out-of-process components are going to become more and more commonplace. And so you can see things are getting harder and harder and harder. But I'm going to keep revisiting this theme that it's really more of the same. It's what's old is new again, just different ways, different configurations. So I'd like to introduce to you the exploit technique conservation status chart. Has anyone here written an exploit before? I'm sure many of you have, if you want to admit to it. Okay, a bunch of you. Some of these might be familiar to you. On the far left there, we have the extinct category. Format strings are essentially extinct, right? You don't really see them anymore. Kernel null pointer dereferences killed a few years ago. NOP sleds are essentially a thing of the past, right? You'll tell your grandchildren about them one day. They were awesome. And then we have our threatened category. Things like stack overflows, they're getting harder. They're still possible, but they're getting harder. Various techniques in this category, vtable hijacking, becoming harder with things like CFI, control flow integrity, JIT spray, JOP, heap unlink, global offset table overwrites. These things are threatened, but they're still possible in some targets. And then, of course, we have our lower risk category, things like memory disclosures, which are essentially free in the Linux kernel, heap overflows, integer overflows, side channels, time of check, time of use, double fetch, type confusion. You might notice that some of these things are vulnerable patterns, and some of them are exploit techniques. And there's a really like gray, fuzzy line between what is what. And I think that's part of the problem, is because we act as an industry more like birthday party magicians than we do professional software engineers. So I'd like to introduce a more sane way of looking at this problem, and really sort of laying out what a proper exploit taxonomy would be. So if we break all this down to a really fundamental level, programs are really just collections of intended state transitions, right? You wrote code, you intended to do things, you compiled it, you have faith that the compiler should have produced all the state transitions that you intended for. But exploit techniques chain together primitives, and I'll talk about primitives in a minute, to add unintended state transitions to a program. That's really what an exploit is. So what's an effective memory safety mitigation? An effective memory safety mitigation places constraints on all state transitions to ensure they were valid and intended state transitions. But unfortunately, program design, which I'll talk about, and languages can work against those constraints. I mentioned primitives a minute ago. What is a primitive? A primitive is really just read, write, and execute, right? If you break this down at like a subatomic level. So all vulnerabilities can be classified according to the primitives they allow an exploit to either control directly or indirectly through influence. And it's important to remember, as an exploit writer, not all primitives require some sort of unintended state transition. So a good example there is like heap spray. If you've ever written a heap spray exploit 10 years ago. There's nothing illegal about heap spray. It's a JavaScript loop that just sprays a bunch of stuff across the heap. It technically is an intended state transition, but unfortunately, JavaScript is untrusted arbitrary code computation by default. And so you can't sort of assume everything that the program will allow you to do. So an effective exploit mitigation would reduce the influence or control of those primitives despite the vulnerability still being present. Defeating an exploit mitigation requires control of a primitive that the mitigation does not impose a constraint on. And so you can imagine things like you have full ASLR in your process, and then you load a shared object that doesn't opt into ASLR, right? There's really no point in having ASLR at that point. ASLR can't enforce that constraint on that particular library. So now let's introduce a more sane version of the exploit technique conservation status. Read, write, and execute, not going anywhere, right? And as long as you think about exploits through that lens, exploits are not going anywhere for memory safety issues. We can come up with all these like cute little names for them, but at the end of the day, each one of these boils down to what is the control or influence you have over a primitive operation like read, write, and execute. And it's also important to remember that sometimes you don't need every one of these primitives. If I can read out the secret cryptographic key from your process, it's good. I don't need arbitrary code execution. You've probably won in most cases. So I mentioned that exploits sort of introduce these unintended state transitions, right? Sometimes we want to go from write to execute. All we have is a write. We don't have an execute primitive. We have to turn that arbitrary write into an execute. A quintessential example of this is a basic stack overflow. We would normally overwrite a saved return address through our arbitrary linear write on the stack. How do we mitigate that? We place a stack canary on the stack that detects the overwrite. So that mitigation imposes a constraint on our write. It requires us to have a read now, because now we have to leak out that stack canary. So in order to get that, we need an arbitrary read, right? So write may require a read. But how can we do that? One good example is, let's imagine a complex process like a browser. And we need to be able, all we have is an arbitrary write from a relative address. Like, what can we do with that? What if we were to write a really long string and then place a C++ object after it, and then do that like 10,000 times, and then use that relative write to overwrite the null byte of the end of that string and then read that string out? What are we going to get at the end of that string? We're going to get the object contents at the end of it in the heap. And that's going to leak a bunch of pointers that tell us where things are mapped in memory. And all of a sudden, we've turned a relative write into a relative read. So we have things like ASLR that try and put constraints on relative reads to make it so it's less reliable. You need a relative read first before you can have an absolute read. So really quick on relative and absolute primitives. A relative primitive allows for read-write from some number of bytes relative to a base address, right? And I'll show you an example of that in a minute. An absolute primitive allows for arbitrary read-write of some number of bytes at an arbitrary address. So here's an example. An absolute write would be similar to the original unlink heap exploit techniques, which used to be called write what where. You could basically write a 4-byte value or an 8-byte value, depending on the architecture, to any place you want in memory. That becomes kind of hard when ASLR is in place, because where are you writing to without crashing? You don't know. And then we have a relative operation, a relative primitive here. An example would be we alloc some memory, 1024 bytes, assign this pointer to it, string pointer, and then using an attacker-controlled offset, a relative offset from the beginning of that chunk of memory, we can write an attacker value. Right, so how can we turn that relative write to achieve a relative read? That was the scenario I just explained, where we could overwrite that null byte at the end of this string and read the values off at the end of it on the heap. So now we start to understand a little bit better of what makes an effective exploit mitigation. I hate to read this off just bullet by bullet, but I'll go through some of these. First and foremost, a good effective exploit mitigation introduces constraints between unintended state transitions. They reduce reliability by removing predictable conditions. A good example of that is ASLR. libc is mapped somewhere different every time, right? That reduces the reliability of exploits that use static offsets. They're usually low cost or invisible to software engineers, right? Like most of us just compile these days, and we take it for granted that we just get a stack canary by default. For those of you who work in IoT and your tool chains still don't support that, I'm sorry. Some of them may be program design specific, and I'll talk about this in a little bit. This is where things start to get a little bit more interesting, and we can't really apply those generic techniques anymore. They might be tied to hardware. We're starting to see the emergence of things like Intel CET to do like shadow stacks for control flow integrity. We see that with like code signing, for example, which limits how much like new code you can introduce at runtime. And of course, the effectiveness of a mitigation, in my experience, is inversely proportional to program complexity. And a good example of that is browsers, where you have arbitrary, untrusted code computation via JavaScript. It doesn't matter how many mitigations you put in a browser, you're screwed. So here's some good examples of some well-known, tried, true, tested memory safety mitigations and the primitives that they impose constraints on. Things like ASLR and PI. I've already explained ASLR. If you're not familiar with PI, it stands for Position Independent Executable. And basically, that's just a way of saying this piece of code or data will always be shifted around in memory every single time I run it. Right? So that imposes a constraint on read and write primitives. And how does it do that? Well, you don't know where to read or write if you have an absolute read or write, because it's changing location every time. Things like heap isolation, which I'll talk about in a little bit. Guard pages, out-of-band metadata, right? So all those original heap overflow exploits, like unlink exploits from 10, 15 years ago, they no longer work because some of that metadata has been moved out of band, and I'll explain that as well. Relro, NX, DEP, right? DEP and NX are huge ones, right? Preventing writable and executable memory. Without that, I'm not sure, so many other mitigations would fall down. CFI and CFG I'll talk about, but those impose a constraint on execute primitives. So we can do mitigations, effective mitigations, by our program design. Things like sandboxes, right? Sandboxes mitigate successful exploits by separating them from sensitive resources. It takes a lot of work to do that, and you relies on the architecture of the operating system to supply you the API calls you need in order to set up a sandbox. So it's both program design and what the system supports. We have interesting new things emerging, like Microsoft Edge's JIT process server. There's a new mitigation they call application ForkGuard that's actually really novel and unique. And what it does is it takes all the dangerous parts of a JIT engine and places them outside of the content process of the Edge browser. If you're not familiar with the JIT engine, it stands for just-in-time, and basically just-in-time compilation of JavaScript code. So you give it JavaScript code, it turns it into bytecode, does a bunch of optimizations, and then spits out some executable native machine code. The problem with that is almost every JIT engine on the planet spits it out into RWX pages, and that's really dangerous. One of the things that Microsoft Edge's ACG doesn't protect against is incorrect JIT code emission, which I'd love to talk about, but I don't have time, so talk to me afterwards if you want to. The iOS mobile Safari JIT mitigation is very, very cool. This was something that Apple did a couple of years back that I thought was really, really novel and unique and forward-thinking. And they used, funny enough, they used a technique that's been in their kernel for quite a while to do this. If you don't run iOS, you're not familiar with iOS, iOS takes the concept of code integrity really seriously. So a JIT engine allocating a bunch of arbitrary RWX memory is kind of scary for mobile Safari. So they did something really smart. They used a feature in ARM called execute only memory. And what they do is they create two mappings for their JIT pages. And they use an API call, a kernel call called mockvm remap, to remap that page within the same process. And one is writable and one is executable. And they keep the address of the writable one secret. And I'll show you how that works. So on the far left there, we have the readable and executable page. This is the first page that gets set up, right? And it's writable to start because we need to put something special into it. And what gets put special in there is a special memcopy function. It actually gets JITted into that page. And that special memcopy function has the address of the page all the way on the far right, which is the readable and writable page. And I'll explain what that holds in a minute. And then we allocate, using mockvm remap, a special page there in the middle that is execute only. And so anytime we want to JIT JavaScript code, we would send it to that special memcopy function on the far left. And it would automatically copy it into that read-write page. And because it's mapped in two separate locations, it would also be in the execute only page. So we've separated out the RW and X page permissions in a really safe and I think creative way. It's a very strong mitigation. General purpose heap allocators are another place where really strong, effective memory safety mitigations have been introduced over the last 10 years. If you've never looked at the internals of like ptmalloc2, and I don't know why you have, no sane person would, but I have, it does some really gross things by default because it's a general purpose memory allocator. And one of those things is it puts metadata at the end of every single chunk of memory that gets allocated. It doesn't understand the types of objects that you're putting into it. And if you're using something like ptmalloc2, and if you're just calling malloc and free, that means you are using the general system allocator. You're probably storing really sensitive secrets right alongside data from untrusted inputs. And I've visually showed that here, where like this is an example of like what the heap might look like. You have a free chunk, and those yellow bars there represent the metadata that goes along with each chunk. You have a free chunk, you have an integer, a JavaScript string, a C++ object, another free chunk. An untrusted input could be anywhere in here. It can be written anywhere. And remember, heap overflows still a problem. So any one of these objects can be overwritten, including things like, Boolean flags that say whether you're a privileged user or not, right? So we need to be able to separate these things out. So a technique called heap isolation started to emerge a few years back. So heap isolation, why is it effective? It separates memory allocations by both type and or size. So we can use that to restrict reads and writes. And let me tell you a little story about Render Arena. This technique, heap isolation, first started to emerge as a security mitigation in Chrome around 2012. And there's a great mailing list post that's public now of the Chrome security team. I think it was like Chris Evans at the time. Discovered that there's this thing in WebKit called Render Arena that basically was like a slab allocator. And all it did was allocate memory for these objects that inherited from Render Arena. And because of that, no one could get use after free vulnerabilities against Render Arena objects to work. No one could get those to be exploitable. Everybody just gave up. And the Chrome security guys were really smart, and they realized, there might be something to this. And so this mailing list post is kind of funny. It's them saying, like, hey, we'd love to use this design and put it in other places in WebKit. And the WebKit developers are like, yeah, we're about to rip that out and get rid of it. So what was born out of this effort was a thing called partition alloc. And partition alloc is really neat. It shipped in Chrome probably about 5 or 6 years ago. It's a general purpose memory allocator, except it has heap isolation built in as a part of its design. And how does it do that? Well, the API is different than just calling malloc. The API is more like, I will create a partition for this type of object, and then my API, I will always pass in the size that I need allocated, or I will pass in the root of that partition and get back a chunk that is only that size. Metadata is never stored in line. It's always stored out of band. So you can consider here like a bunch of C++ objects that inherit from one base class called base. You could create a partition in partition alloc that is specifically for objects that are inheriting from type base. And that's basically what Render Arena was, except this is the generalized version of it. So here's a visualization of what partition alloc really looks like. All the allocations are the same size, and they're either free, or it's an allocation of an object that inherits from base. And unfortunately, I don't have enough time today to explain why this makes like use after free exploits really, really difficult. I basically can boil that down to, normally you would want to replace one of these objects with a JavaScript string, except JavaScript strings no longer get allocated in this heap. They're in a separate heap just for JavaScript strings. So you can't easily replace these types of objects, right? So this is how heap isolation and partition alloc in general is an effective memory safety mitigation. And I liked partition alloc so much that I forked it, ripped it out of Chrome, and added a bunch more hardening to it. And I call that hardened partition alloc. I won't go through each and every one of these today, but I added a bunch more hardening to it, like free list randomization and better double free detection, delayed free, and all things like this that make browser exploits a lot more difficult. It's on GitHub today if you want to check it out. I've been talking since the beginning of this about how program design can really affect how effective or how strong your memory safety mitigations are. And one thing that always bothered me about fork is that it basically makes ASLR and stack canaries kind of useless, right? You can easily defeat them in a program that uses fork. And most server systems, most servers are going to run daemons that follow this Unix forking model, right? Everyone's running Linux on the server side now, right? I'm sure there's a few guys at Apple who think Darwin is going to make a comeback, but so things like Nginx only scale because of fork, right? Because of the mechanics behind copy on write. And so how does fork actually weaken stack canaries in ASLR? Well, if every time you connected to Nginx and you had a stack overflow, and you were able to keep trying over and over and over again because it kept forking and spawning a new child process to deal with your exploit payload, you'd get unlimited tries to try and brute force the stack canary. And you can do that byte by byte by byte. And you can defeat ASLR in the same way. There's an exploit technique out there called blind ROP, which, again, I don't have time to go over today, but it's a really cool technique that allows you to basically extract a closed source binary. I'll talk about it in a minute, so I won't dive in too deep right now. Yeah, so anyway, I came up with a partial solution for forking daemons and defending that kind of program design that I call ForkGuard, which I'll talk about. But one of the main driving forces behind developing ForkGuard was basically the blind ROP technique, and of course the fact that it makes ASLR and stack canaries weaker. Basically, stepping back, ROP, return-oriented programming, reuses existing code pages to stitch together new payloads. And you basically need ROP in hard targets today because you can't just allocate shellcode in readable, writable, executable memory. So BROP is blind return-oriented programming. It's basically a technique for brute forcing a daemon and over time guessing the stack canary and then guessing where the write syscall is mapped and then leaking the rest of the binary over the existing network socket. And this is actually, there's a really cool POC for this that was used against Nginx a few years ago. And so it works. And it's a little loud, but you only need to do it once, right? Let's say you have an IoT device and you've hardened it reasonably well and you can't get a shell on it, which I know is not true for like all IoT devices. But anyway, let's say we got to that point in the future. All you really need to do is extract that binary one time in your lab. And now you have the binary to basically analyze and find other sorts of vulnerabilities in. And I wanted a way to sort of kill that. So I developed a custom mitigation called ForkGuard. Which is basically just a shared object that you would load into your closed source process. It doesn't matter, you don't need source code to do this. You can be working on a closed source binary or something open source you compiled. You would load it with LD preload, which tells the linker to load it before any of the other libraries. And basically what it does is it loads a whitelist of functions it knows that the child process needs. And then through dynamic linker introspection, discovers all the other code pages that the child process will need. And the way it does that is it overloads libc's fork call, and it uses madvise, and I'll talk about this. But essentially what happens when a process forks is the parent process image gets basically cloned and turned into a separate process. That's the child process. And when that happens, all the memory that was in the parent process gets shared into the child process, but not all at once. As the pages get accessed, copy on write kicks in, and those pages get mapped in. But at the end of the day, all the pages are still there. And so why, like when you start up Nginx, for example, all that initial setup code used to like start up the daemon, open the sockets, all that stuff, like why is that needed in the child process? It's not. It's not needed at all. But it's definitely useful for ROP payloads because it's code in memory you can reuse. I wanted a way to trim down that code in a child process, but maintain the exact same performance that Nginx has and relies on, gets through using the fork model. And I did that through using a combination of madvise and some tricks with dynamic linker introspection to discover which code pages the child actually needs through trial and error. And so the way this works is the parent process starts up, hooks fork, reads in its whitelist, uses all the dynamic linker structures in memory, discovers all the code pages, discovers which ones the child process needs and which ones it doesn't. And then it uses an madvise syscall, and it tells the kernel, hey, this page at this address, if this process forks, the child doesn't need it. So never copy on write it. And so in the child process, when we start up, if you were to use an untrusted ROP payload or try and use a BROP technique, you would basically just crash because those pages aren't mapped anymore because the child process doesn't actually need them. So for me, this was a pretty big win. The naive implementation, which only took about a week to write, resulted in like 35% less code pages in Nginx. And it makes blind ROP take way longer, like an order of magnitude longer, and you never actually get the full binary off of the system because it's been unmapped from the process you're exploiting. And it works on closed source binaries too, which is pretty cool. There's a few other things about program designs that make memory safety vulnerabilities weaker in some cases. ASLR is a good example in a 32-bit browser. It's essentially worthless. right? All the side channels aside, the memory space is just not big enough, right? Heap spray, you can basically fill up all the free space in a 32-bit browser with heap spray, and ASLR just becomes completely ineffective. ASLR in a 64-bit browser provides a little bit more value, right? There's always going to be things like side channels and JITs and things to leak those addresses. ASLR in a standalone program with no scripting environment and a non-executable DEP mitigation in place actually provides a lot of value and is not very easily bypassed. You don't see people like throwing exploits at reverse caching proxies every day, right? Because it has these mitigations on, and they're actually fairly effective in that type of an environment where you can't reprogram and you can't introduce a bunch of unintended state transitions. DEP is, of course, highly dependent on ASLR. These things, it's important not to think about them as like a chain of mitigations, but more of a mesh of mitigations, and they all work together. DEP would be kind of useless without ASLR and vice versa. Of course, because ROP provides a very easy alternative to shellcode. And without ASLR, ROP payloads are essentially trivial to construct because they're always in the same location every time. Of course, this is the only time I really talk about kernel mitigations, but kernel address space layout randomization is essentially useless. And the reason for that is that you're already on the system, usually, when you're trying to exploit a kernel vulnerability, and the kernel will basically just tell you where everything is mapped all the time. Right? It leaks structures all over the place and uninitialized memory all over the place. So ASLR in a browser, slightly effective. KSLR in a kernel where you already have local access, not very effective. I talked a lot about browser designs, right? They actively subvert very simple mitigations. Untrusted arbitrary computation of JavaScript basically means all state transitions are intended by design because you can do anything you want with JavaScript. We talked about stack canaries and things like that. Also, if anyone has ever written anything that linked against libpcre, you have RWX memory in your process right now because it has a JIT and it was written a long time ago. C++ languages definitely change the game for effective memory safety mitigations. If you write a lot of C++, you know that polymorphism is just a standard way of writing C++. And it's also a fancy way of saying you use virtual functions with a bunch of classes that inherit from a base class. And that introduces behind the scenes a thing called a vtable pointer, which sits at the base of your object in memory. And it's a very attractive target for an exploit writer because once you can overwrite a vtable pointer, you can basically get arbitrary code execution. And so we need mitigations in place to protect against that. And we have that today in control flow integrity and control flow guard, which are two emerging mitigations that are fairly effective. But we can break these down into different types of CFI. First, we have coarse-grained CFI, which is a little naive. This is more like the Microsoft implementation, which you can find referred to in literature as control flow guard, which is basically a bitmap that represents all the valid call locations. Which is fine, and it is useful because it makes some ROP payloads no longer work. But you can always use things like counterfeit object-oriented programming. You can stitch together other functions and still get arbitrary code execution. A good visualization of that's the player on the top right, right? It basically just means as long as you're calling a valid function somewhere, it's allowed. And then we have a better form of CFI, which is implemented in Clang, called fine-grained forward-edge CFI, which is a little bit more strict. And that graph is enforced explicitly according to the call graph that's computed at compile time. And it looks more like there on the bottom right, where only these intended state transitions are allowed. And those are enforced at runtime by pieces of code that get compiled into your final binary. And we have other things emerging, like fine-grained backward-edge CFI, which will verify that a function is returning to a function that it's supposed to. We've seen this in the past in things like shadow stacks. But the problem with that is shadow stacks themselves live in user space and they are subject to memory corruption. Sorry. In the future, I think we're going to see things like Intel CET, which do shadow stacks in hardware, which I think will be more reliable. So mitigations become more effective when combined together to form a mesh. I talked about this before. ROP defeats DEP, but requires an ASLR bypass. So if you have both, it's kind of a catch-22. You need both a read and a write primitive. So what makes CFI and CFG so strong? It enforces the intended control flow of the program. But it's not as strong without strict type checking and pre-computed order of operations, which you don't get in things like Microsoft's Control Flow Guard. But you do get if you enable Clang's version of CFI. And of course, there's a lot of challenges with rolling out new effective memory safety mitigations. I know a lot of you here probably work in the embedded space. And I joked before, but it takes years and years and years for embedded tool chains to catch up with like mainline Clang. So even getting really basic stuff like stack canaries takes a long time. Things like heap isolation is not as common because sometimes you don't have a heap. You just have one stack and a bunch of global memory. So the widespread adoption of effective memory safety mitigations can take a long time. And unfortunately, new exploit techniques are adopted like within 24 hours. New code often reintroduces problems of the past. We see this all the time. About 2 years ago, I reported to Chrome when they replaced part of their JavaScript heap with a thing called OilPan. They basically reverted backwards to 15 years ago and put a bunch of inline metadata in line with the heap allocations. And it took about 2 years for them to figure out how they could move that out and protect it in a way that didn't actually hurt performance and cache locality. And that was brand new code from a team who really does know what they're doing. And then there's things like engineering time trade-offs. Anyone here is familiar with Google Native Client? It was amazing. It was rock solid foundation security. Unfortunately, it was like writing ActiveX in like 1995. It was awful. No one wanted to do it. Isolated heaps introduce a little bit of overhead in the sense that you can't just call malloc free anymore. The API is a little bit more complicated. We have performance trade-offs. Things like full CFI do have a measurable performance impact, which matters in some cases. So you can't just put them everywhere. ASLR, thankfully, has almost no measurable performance impact on modern hardware. Unfortunately, it has almost no measurable security impact in most cases. So with that, thank you for listening. And if you have any questions, I'm happy to answer them now or after.